Hello, everybody. Hope you had a nice lunch. Okay, so I will be talking about some of the recent work happening at IBM towards fault tolerance. At this workshop last year, my colleague Blake came and he talked about our software that you probably all know about, Qiskit, and performance improvement in Qiskit and things like this. So for this year, rather than repeating those stuff, I thought I'll talk about something completely different and quite timely because there have been a lot of talks on error correction in this workshop. Basically, I think, so what I will do is my talk is sort of in four sections. First, I will describe the family of quantum error correcting codes that we're interested in and we're trying to build hardware for, what they are and what motivates us to pursue them. Then I will talk about what it takes for the quantum hardware to realize those codes and some of the experimental progress we've made along those lines. Then I will talk about how to compute in these codes. So what are the native instructions set in this code that we can express and we can compute in them. And then lastly, how do you take your favorite circuit and compile it down to run on this type of architecture? And so I guess my takeaway for all of this is that because it's a software forum, we do have software. It's a little bit not greatly visible, but it's called Bicycle Architecture Compiler. So if you search it, there is open source. And hopefully after the end of this talk, you'll be motivated to go try it out and maybe contribute to it because it's all very new work. But yeah, so we call this architecture the bicycle architecture because it's based on bivariate bicycle codes. And so I guess the main motivation behind pursuing these types of code, which is a quantum LDPC code, is that you might all be very familiar with the surface code. The surface code has been around for 20 years. A lot of people have studied it at great lengths, and we understand a lot about how to do computation in it, and many things have been optimized for a surface code. And it's great. The surface code, it has, there's great motivation behind it. It's realizable on a nearest neighbor 2D lattice architecture. It has a very high threshold. The biggest downside of the surface code, however, is that it takes a lot of physical qubits in order to realize one logical qubit. And we heard about this yesterday as well from Jens. Basically, like if you have a L by L lattice, you get a code distance of L, and so the number of physical qubits that you need to put into your quantum processor in order to increase L or to increase the number of logical qubits increases quite rapidly. And so the main motivation behind pursuing these higher rate codes, higher rate meaning they can encode more logical data with the same amount of physical data, is that it's expensive to build qubits. It's hard to put them all in a fridge, cool them down, wiring. It's just generally hard to spend a lot of to build a 1 million qubit quantum computer. There was a Nature paper from the IBM group a couple of years ago, or maybe last year actually, that introduced these bivariate bicycle codes. And as you can see in this plot, so the red is this bivariate bicycle code that is a distance 12. So this one realization of it is a distance 12 code that encodes 12 logical qubits inside 144 physical qubits. And these are circuit level simulations. The blue and green are sort of comparable surface codes for comparable code distance and same number of logical qubits. And you see that they have a similar performance in terms of how much suppression of error they give you. But the LDPC code has a factor of like 12 improvement in the encoding rate. So with 144 qubits, you can realize 12 logical qubits at a code distance of 12. Okay, so of course you have to do something to get to this, right? So there's the downside of it is that you have to do a better engineering or make a better chip or a more complicated hardware. So you might be familiar with the surface code, right? Like it's laid out on a 2D grid where everything is interacting with north, west, south, east. Here, what you get on top of that is that you need to have some long-range connectivity where you have the same lattice. The degree 4 lattice is the one in black. It's the same as the surface code. But on top of that, every qubit is connected to 2 more qubits that are a few lattice sites away. So basically, all the qubits are degree 6 rather than degree 4. And instead of being everything nearest neighbor, 4 of them are nearest neighbor, 2 of them are long range. Okay. So then you might ask, well, isn't this very difficult to make on a superconducting hardware, right? And it's true that historically, like superconducting hardware, it's been constrained to nearest neighbor interactions. However, we saw a nice talk this morning from IQM where they showed, better connectivity and how you can engineer higher connectivity and maybe longer range connectivity. It's the same story for us. So we've been hard at work demonstrating the key ingredients or pieces of this architecture. So here's one hardware demo. These are small scale demos, and the goal is to integrate them into a large chip. But for this is a 7-qubit quantum processor where the middle qubit is connected is a degree 6. It's connected to 6 other neighbors, and you see that the error rates are kind of state of the art. Like they are basically quite close to what we get in our more sparse hardware. Similarly, as I said, some of the connections have to be longer range. Here's another hardware demo where we have this tunable coupler connecting 2 superconducting qubits and increasing the length of the coupler progressively from top to bottom. Again, we see that the error rate does not suffer that much. So the error rate is all in the same ballpark. So we feel that we understand the hardware and the tunable couplers well enough that we can engineer these things, like the higher higher degree of connectivity, longer range connections. And then the other thing about this lattice that I described is that it's not a planar lattice anymore, right? So with this degree 6, you have to your degree 4s can be all in a nearest neighbor lattice on one plane, but you need a second plane in order to not have wires crossing each other. So it's a biplanar architecture. So it's relatively okay, so it's the best thing you can get out once you start going to more. Because, for more complicated, there are other quantum LDPC codes that require, more planes, a thicker hardware graph. For us, we only require a biplanar graph. And here's another hardware demonstration. This is feasible as well, where basically, this bottom connection is happening on the bottom plane. And then there is another layer of interconnect that is happening on top of it. That red connection is basically it goes out of the plane, travels, and then comes back. So this is this long range connectivity between 2 qubits that are far apart. And so we can break the plane as well using these techniques. Okay, so these are some of the ingredients that we need in order to realize these codes. But so what we're interested in here in this talk is, okay, once we have all of these things, how can we build an architecture out of it? Okay, so as I said, so let's just focus on one instance of this family of code, which is the 144.12.12. So basically, one code block, you can think of it like one of those donuts, and consider that as a single chip. Okay, so I build a chip that has 144. It's actually more because there's ancilla to measure, so it's like 288 actually, so considering the ancilla. But of the order of like 300 physical qubits, encodes 12 logical qubits, so let's call that one donut or one code block. And then we can put a bunch of these next to each other, right? So another code block could be the next set of logical qubits, the next set of logical qubits. But then you have to connect between these code blocks, these modules. The nice thing about it, though, is that this modular architecture, one big problem in superconducting hardware is that the yield of the processor is not perfect, right? So you build your hardware, you build the qubits, and you design it for to meet some criteria, and then you try to manufacture it to actually tape it out. There's a finite probability of failure for each of these links, each of the couplers, each of the qubits. And so, if you make a gigantic chip like this, like a monolithic chip with thousands of qubits in it, the probability that it actually yields, it kind of goes to 0, right? So there's a big benefit to having this modularity where you can basically break the problem down, make it one chip that has 300 physical qubits on it, another chip, and then you can tape them out separately. If something is broken, you throw it out and try it again. You can do the similar thing for surface codes as well. Of course, in surface codes, you also don't have to make everything in a planar lattice, but because the encoding rate is low, you will have more of these connections between chips in that scenario. Yeah, so let me also talk a little bit about how to connect these different modules. So this is the architecture that we're envisioning. So again, consider one of these donuts as a code block encoding 12 logical qubits with 300-ish physical qubits. And then, so that itself is just a memory, right? Like that just gives you the memory. But if you want to compute with it, there's an extra gadget that we call the logical processing unit, or the LPU. Essentially some extra qubits that is added to the chip. What they do is that they allow you to measure certain operators from the code. So the X and Z measurements. And then there's a bridge system. So there's yet another set of ancilla. I will talk about how big each of these are in a second. The bridge system, what it does is it allows you to connect one module to a separate module. And the connection happens through what we call an L coupler, or a long-range coupler. Because as I said, each of these is contained within one chip, so one chip here, one chip here. They're still within the same fridge, right? So 300 qubits, that's completely feasible within one fridge. But you have to connect them, and you have to connect them using some longer range couplers that are quite different from those on-chip couplers that connect the neighboring qubits. Again, so that itself is another engineering challenge. But in a second, I will show you, some experimental progress again for that as well. But then you can basically just duplicate this and make a bigger architecture, right? So like imagine an architecture where I have a bunch of these donuts, each of these 12 packs of logical qubits next to each other in a line. Each of them encodes the memory, like in the donut itself. The LPU, or the logical processing unit, is the one that enables computation on it. I can measure certain operators, and those measurements allow me to perform, for example, certain Cliffords. And then if I want to do a non-Clifford, we have to couple this to a magic state factory, where the magic state factory supplies T-gates, but then with gate teleportation or injection, I can basically move the magic state factory to perform non-Clifford operations on each of these donuts. And so that basically, this is an architecture for universal computation, right? It's modular, so it's nice to build in the sense that you can focus on each of the chips separately and then kind of connect them to each other. It is universal because I can do the Cliffords and the non-Cliffords, and the encoding rate is high as well, right? So I can get a lot of logical qubit inside it for a good number of physical qubits. So as I said, let me also just describe a little bit about those L couplers. So this is again one demonstration of this. So the cartoon picture that you see at the top, those are kind of 3 payloads, but within the same fridge. But they're physically quite separated from each other. And so this is a particular demonstration of this, where we took a cable that is a superconducting wire, basically, that is 1 meter long. So it's very, very long in the scale of things, right? So if you remember what I showed here, on the on-chip couplers, they're like millimeters, right? So this thing here is 1 meter long, so much, much bigger. But again, we were able to demonstrate, this is the first demonstration, so we got a fidelity of around 96, 97% out of it. So it's not what we require for it to do the logical computation. This has to improve. But it shows that in principle, like on a length of wire that is 1,000x larger, we're still able to get reasonable fidelity for that first demonstration. And again, this is being actively worked on. Okay, so hopefully by now it's clear how the bicycle architecture works, right? Like we have these 12 logical qubits encoded inside one of these modules, one of the code blocks. We have an LPU, or a logical processing unit, that allows us to measure certain things from the code, that lets me do Cliffords, and then a magic state factory that supplies the magic and lets me do universal computation. So then you can make different architectures out of this, right? So the simplest thing that I showed is just a linear chain of these, so like a code block 1, 2, 3. The U describes the LPU, that system that allows me, that ancilla system that allows me to measure operators from the code. A is the bridge between the two, and the factory is the magic state factory. And here's a rough sense of how the number of physical qubits that goes into each of them, right? So for example, for the code block, as I said, it has 288 physical qubits. So look at the gross column. The gross code is the code that I said, 144.12.12. There's another version of it, the 2 gross code, what we call. There you have basically a higher distance. So if you're really interested in doing a very deep computation, well, you need to go to a higher distance. So this one has a distance of 18, but it has more physical qubits, obviously. But okay, so if we just look at the gross code, it has 288 for the memory, 90 qubits. So the ancilla system that does that the LPU is in, it's relatively small. Like it's just some extra qubits, 90 extra qubits. The bridge is also pretty small, 22 extra qubits. And then the magic state, right now we're basically just using the surface code as a magic state factory. There's some active work to design native magic state factories within the bicycle code. Any questions? Okay, yeah, feel free to interrupt me at any time. Okay, so and then you can basically connect them in different ways, right? So like there's a triangular connection in the second picture, etc. But what I'm interested in this talk is basically how do we compute in this architecture, right? And how do we compile for such an architecture? So here's an illustration of the type of instructions that you can do natively in this code. So imagine, so it's kind of complicated, I will try to walk you through this, but imagine one of those donuts, I said is 12 qubits, right? So you can break it down into a 6 and a 6 block. One qubit per sub-blocks is dedicated to, we call it pivot qubit. That's the qubit where the ancilla system or the LPU is connected to. And so this allows us to do measurements inside this code of certain types. So you can measure any operator between qubit 1 and qubit 7, which is the first pivot qubit of each of those subblocks. So I'm talking about here, right? So 6 qubits here, 6 qubits here, together they make a donut. And I can measure, for example, Zi between these 2 qubits, okay? Or, for example, Xi between these 2 qubits. There are certain automorphisms that you can do, but which is basically just shifting physical qubits on the torus. This realizes some kind of a low overhead unitary for you. I'm not going to talk about that too much for now. And then the other thing you can do, so these are in-module measurements, so you can do an in-module measurement of Zi or Xi or whatever. But you can also do measurements between the modules. That's that bridge system that I discussed, right? So the inter-module measurements, they essentially, for example, you can measure a ZZ between 2 code blocks that are separate. Where the Z is supported on logical qubit number 1 of block 1 and logical qubit number 1 of block 2, for example. And there are certain so there are intra-module and inter-module measurements that you can do. But that's it. So you can do inter-module measurements, intra-module measurements, and you can do magic states. Magic states, it works the same way. So imagine you have a factory, it pumps out a magic state for you. The way you teleport it is you grab the closest module to the magic state, which is this bottom donut, let's say here, and you do a ZZ measurement, and then you kind of measure that out, and you can do some corrections in order to teleport this here. So given a combination of intermodule and intramodule measurements, I can basically do these types of operations. But looking at this is very hard to see what's happening, what kind of a computation is doing. And so for the rest of the talk, actually let me quickly just recap also the error rate. So there's been an extensive circuit level noise simulation for these different instructions to sort of see their performance. Here it is. Again, if you go to this archive link at the bottom, it has a lot of details about all of these. But just to highlight a few things, so these have been done for gross code and 2 gross code at physical error rates of 10 to the minus 3 or 10 to the minus 4. Of course, our target is to get to around 10 to the minus 4 physical error rate, because then the logical error rate becomes much better. But the thing you can see here is that by far the most expensive thing you can do is this intermodule measurements. You can see that it's several orders of magnitude more noisy. And this noise is basically your budget of computation, right? As your computation proceeds, it's picking up these logical error rates as it goes along. And so that kind of puts a cap on the amount of logical computation you can do before there's too much noise. Okay? But that's it. The instructions is you can do idles, you can do automorphisms, you can do in-module measurements or inter-module measurements. Okay. So now we want to actually take some arbitrary circuit and lower it to that kind of an architecture that I described, right? So here's a summary of how this thing works. There's a lot to it. Again, in the paper, you will see all the details. But I will focus on parts of this diagram just so you can get a flavor of how the compilation works. And as I said, the compiler is open source. You can go see all of this. But basically, the way you start the compilation is that you start with a circuit that is expressed over Clifford plus phi rotations. Okay, so this is a circuit that you can get in Qiskit or any of your favorite tool. This is a universal gate set, right? So you have Cliffords and a bunch of, let's say, RZ phi rotations. And then let's just say we have a bunch of those, and then you measure the output in a Z basis. Let's say that's just your standard circuit. The first thing you can do is that you can, if you just recall, right, like we had, I showed you that basically in the architecture we can do measurements, and these are measurements that are Pauli measurements. So somehow I have to do a few things to go from this picture to a picture where everything proceeds by measurements, like measure an X, measure Y P1, measure ZZ, blah, blah, okay? So the first thing I do is I take the Cliffords and I push it all to the end of the circuit. You can always push Cliffords through Paulis, and what it does is it conjugates the Pauli to become some other Pauli. So you basically, your circuit, what it becomes is, it is a series of like Pauli rotation 1, Pauli rotation 2, Pauli rotation 3 with different angles, phi 1, phi 2, phi 3. And then that Clifford comes at the end, right? And then the last thing you can do is you can absorb the Clifford into the Z measurements, which becomes another measurement. In the notation, every notation that I have in these slides, the round boxes are rotations, and the square boxes are measurements. Okay, just like so that we can distinguish what is a rotation versus a measurement. So you have a bunch of Pauli rotations and a Pauli measurement at the end. Okay, so now we need to lower these to what the bicycle architecture understands. So imagine you have a bunch of logical qubits distributed in these donuts. So like qubits 0 to 11 here, 12 to 23 here, etc. And then imagine this last one is connected to a magic state factory. So what I will do in the next few slides is I will just describe this expansion to you, okay, and some of this bottom expansion. But the rest is kind of also similar, but also in the paper, okay? Any questions so far? Okay. Yeah, as I said, the round boxes are unitary or rotation gates. If the color is blue, it just means it's a Clifford. So the angle is pi on 4, or pi on 2 in some conventions. And then square boxes are measurements, okay? Let me just skip this part. Okay, so what I said I would do is I will describe this, right? So this, how do I go from a Pauli, which could be this could be like a 100 qubit Pauli rotation, right? So it could be like, yeah, just a Pauli supported on 100 logical qubits with some angle phi. How do we put it onto this architecture, which is modular at different code blocks, do their own thing? So you can start with this circuit identity. So if you have a Pauli rotation, which is defined by this equation here, you can implement it by an ancilla, by basically putting the ancilla in the plus state, this is kind of a phase kickback circuit identity, if you've seen it before. You basically, instead of doing the rotation here, you do the rotation phi on the ancilla. Like you go in that basis, you'd rotate in that, and then you measure it out, and probably you have to do some corrections as well. But this allows me to take this rotation, which was supported on 100 qubits, and just make it a single qubit rotation x, around the poly x. And then this poly just becomes a control poly, like a proper poly, not a poly rotation. Okay? So after you have that, as I said, this P could be a big P, right? So let's factorize it into P1, P2, P3, such that these can then be put on different code blocks, different donuts. You can do the following. So imagine this P, instead of doing control P, I do control P1, control P2, control P3, which is the same thing. But now there's a trick that you can do, which is instead of using the same qubit for the control, you can distribute the control. So by doing basically preparing the state here, doing these C-naughts, then you can distribute the control, and you can perform these control P1, control P2, control P3 in parallel. So now, so what is this thing that I made? This state that I made is basically a GHC state, right? The trick is take that control, distribute it across the code modules with as a GHC state, and then everything becomes local to the code module, right? Because we want to operate within a donut or a code module. Yes. Yeah, the pivot qubits are not going to participate in computation. So actually, yeah, you are sacrificing one of your 12 to just be clean space, yeah. So yeah, so this is a GHC state that you can also prepare. So as I said, I promised to take everything into the language of the bicycle architecture, which is just a bunch of poly measurements. So you can realize a GHC state like this. So you can just, so prepare a bunch of plus states, do ZZ and ZZ measurements, measure their parities, and you've made a GHC state. So once you make the GHC state, this is the only thing that requires inter-module measurements. If you remember that terminology that I showed, that the most expensive thing is the inter-module measurements. But essentially, like, you distribute a resource across these donuts or across these modules as a GHC by doing inter-module measurements. But then after that, everything becomes localized to the donut, localized to the module. So like the rest is, we're just going to pay the price of intra-module measurements, in-module measurements, which is cheaper. Okay, so I did this, I make the GAC, and now I have to make a bunch of controlled polys within a code module, right? This is how this proceeds. So if we go back to the original, what I had originally, like the phi rotation that I wanted to make, we made it into a GHC. This is just half of it is described here. Followed by in-module control P1, and then potentially, or really a X phi rotation, which also has to be synthesized. But everything here now is within the module. Okay? So how do we implement this controlled poly? Here's a circuit identity for that. So if I have a control poly, it's a unitary, but it's a Clifford unitary because it's a control poly, right? As I said in my notation, blue is Clifford. So you can always write it like this. And then here's just a bunch of circuit identities. You can move this measurement, commute it through. You can absorb it into. You can go past this X. It becomes a Y rotation. Absorb it into this measurement, and then yeah. So let me just keep going. This final rotation, the only rotation. So everything became measurements so far. We're progressing to make everything measurements. There's one rotation here left, ZP1. This ZP1, here's another circuit identity, which is that if you have two anti-commuting polys, here's like you can basically make the QR rotation into a measurements of Q and R. So this is what we do here. So this is ZP1 rotation. I replace it as this identity. It becomes a YP1 measurement. So now we're basically done. So all of these became measurements. This P1, because it's just a poly rotation, you can kind of just not do it and remember it and keep going. Like move it through the circuit by just updating Clifford frames. Or you just have to do poly tracking. So the only thing left is this, is two things. I made this into a measurement, but this is not a native measurement to the gross code. So we have to do some more things to make this a native measurement. And the other thing is this rotation, you have to do synthesis, right? Because this is a non-Clifford. And so you can do a Ross-Selinger style synthesis and expand it out as a bunch of Hadamard's and T-gates. And so those are the ones that have to be realized with the magic state next to it. So each of the T-gates, for example, you have to do an inter-module measurement with the magic state factory. So I won't describe this one. You can see the paper for more details. But let me just finish this by saying that how to make this particular measurement into a code-native measurement. This is this one at the bottom. So if we recap, we start with a phi rotation. We distributed it over a bunch of modules using a GHC state. Everything became a bunch of X on the ancilla, a bunch of YP measurements, YP1, YP2, YP3. And then followed by this rotation, which has to be synthesized with the magic state factory. But as I said, this YP measurement is not native. So this itself has to be expanded as the following. So what you can do, there are a bunch of rotations that you can do natively that you can on the gross code. And so all you do, you just conjugate this YP or YQ poly by these Cliffords, which are essentially 11-qubit Cliffords. We can make all of those 11-qubit Cliffords. So you can just conjugate them in order to reach a measurement that is now native, and then you implement that. So it's kind of complicated. Basically, everything gets expanded into more and more, but that's what the tool is for, and that's what the software is for. Let me see. Okay, so this is kind of a distribution of this conjugation that I described. Like you start with a poly measurement that is not native, but you're going to conjugate it by some Cliffords that are native, and then this becomes but the question is, what is the shortest sequence that you can conjugate? So we did a search over this, and this is the kind of distribution of number of in-module measurements that you need to do to realize all the possible, those control P's. I guess the median is around 19 or something. That's the number of rotations that you have to do in order to realize one of them. Make a non-native rotation into a native rotation. But again, all of these are in modules, so they're relatively cheaper compared to inter-module. Okay. So this is what as I said, we have tools for this. The other thing that I maybe didn't mention about these tools for fault-tolerant architectures is that they have to be very fast, because the point of doing fault-tolerant architectures and compilation and resource estimation is that if error correction is successful, we're going to have error rates of 10 to the minus 9, 10 to the minus 10, right? So that means gigantic circuits of like billions of gates in them. So it has to be able to handle a circuit that you throw at it with billions of gates, and to do this kind of expansion and to derive the resource estimates. And so this is designed for this exact thing. It's a streaming compiler. It never actually loads the entire program in memory. It kind of reads incrementally, and it does this expansion on the fly. And then it does this resource estimation for you. So here's the upshot of all of this is I started the talk by saying the BB code, or this gross code, which is one instance of it, they're very efficient in terms of encoding rate, right? And so this is exactly what you see here. So on the x-axis, we have logical qubits. On the y-axis, we have t count. And then, as we move in this diagonal up, you get more and more complicated applications and algorithms, like quantum phase estimation might be here, Shor's algorithm, and then you might have like other problems that are maybe like scientific, like Heisenberg model, whatever. And so the black squares are resource estimates for what a surface code architecture would be able to do. So for example, let's say you build a chip with 50,000 qubits in it. That's all you get, like you have budget for. You built a chip, hopefully more than one, like a bunch of modules, but 50,000 in a fridge, let's say, and the physical error rate, let's say, is 10 to the minus 4. So this is what you built. Now, if this thing is running a surface code, it can do this amount of computation. If this thing is running the BB code, it can do this amount of computation. Okay, so you get you get quite a big saving in terms of the number of logical qubits that you can get from your processor for the same amount of physical qubits. There is a downside to it that there's more about this in the paper, which is that the rate of computation gets a little bit slower in the sense that, so what we've done here is that we've packed the information quite densely, right? So kind of there's a fundamental limit in like the addressing of the logical qubits, so the addressing becomes slower. So you will see, like, if you look at the time of computation, it does become longer, but the space definitely shrinks. And I think there's more work. For example, the compilation that I showed is kind of a baseline compilation. There's a lot to do in the compilation to make it shorter or more parallel, for example, which can improve the runtime. Okay, so I will just conclude by going back to the criteria that I started out with my talk, which is like, you want a fault-tolerant architecture that is universal, you can addressable, you can compute on the different logical qubits, you can do universal computation, and it's modular. And this architecture ticks these boxes, but also I will also just say that there's a lot of opportunity for improvement. Like as I said, the surface code has been around for a very long time. People have studied it at great depth. And so there's a lot to be done here, and our understanding of a lot of these things, like doing better magic states, or the compilation itself, like the compilation that I showed is very serial, actually, like this way of doing polys. A lot of these can improve, and they will result in better resource estimates as we go along. Thank you. If you have any questions, let me know.
Thank you. Thanks, Adam.